Welcome back, champions of Leetcode. My name is Constantine, and today we're going to go through a problem, all nodes distance k in binary tree. This is a very interesting problem just because it involves a little bit of thinking, and it's also a common problem given in numerous interviews. So let's go through the problem description. We're given the root of 8 binary tree, we're given a target, and we're given a integer k. In this case is 2. So we want to return a list of integers which will contain all the nodes values which are distance k distance from our target. We can return the answer in any order, so they do not care about the order, which is pretty good. So let's go through this tree right here. So let's think about it. If this is our target right here, we're returning 1, 7, and 4. And this is our k, which is equal to 2. So you can see, like, from this 5, if we're moving 1 step and then 2 steps, we're getting to this 1, and then 1 step here, and then 2 steps, 1 step, and then 2 steps. So that's why we're returning these 3 nodes right here, right? So how can we do this problem? We know that main traversals of a tree are DFS and BFS. So which one do you think you would be more suitable in this case? And take a moment, pause this video and think about it, because this will give you the right intuition if you think about it. And if you chose BFS, I would say you're kind of like on the same opinion with me. Just imagine this. If you have a graph like this, a matrix, and you have a dot right here, and you need to find its neighbors. So you know that DFS would go all the way, you would choose one direction and you will exhaust all that direction. And you could go either direction you choose. But BFS, since it's a level order traversal, it's gonna go like in circles, right? So it's gonna go like that. So that's why in this case, it's easier to say that for us right now, if we're doing a BFS starting from this node, from our target, the first level basically will be this, right? Because these nodes are one level apart, but we need k equal 2. So then all we can do is just imagine that we're getting another node, another level. So then all we have to do is just return 1, 7, and 4 in any order. So you see how we can do that with the BFS, and we can do this with the DFS as well, but I think it's so intuitive, or at least it was for me, to think about this problem in a BFS traversal. Good. So now how can we do this? We know that since this is a binary tree, we know that we could go down here. So if we start at this 5, we could do a normal BFS and we could get to this, right? This is just 2 levels down. But the only challenge here, and what makes this problem interesting, is that we need to add this too. So somehow we need to go up and then down again. But this is a binary tree, so we can go up, right? We don't have an access to this parent. We only have access to the children. So I think this is the main thing that we need to figure it out. How are we starting from this 5, how are we getting access to the parent? We also need to go up. Like if this would be our target and k would be equal to 2, we would need to go up 2 levels. So you see, I think this is the main challenging. Right now, imagine the binary tree. The arrows are always down because we have access to the children only. So we need these arrows to be upwards too. So how are we going to do that? The easiest way to do that is create a hash map with the values where this 5 right here is going to be our key and the value itself is going to be our parent. So, and once we get to this one, again, our parent is 3. Once we get to 6, our parent is going to be equal to 5. Once we get to 2, our parent is going to be equal to 5, and so on. Once we get to 7, our parent is going to be equal to 2, and so on. So once we have this hash map built, then we could just look in the target, and whatever we find this key equal to our target, which in this case is this one right here, we could easily go to the parent. And for example, if this would have had something higher, we would just look into that, we would look in this value, and then we will look it again in our key, and then in this way we could just go upwards as many times as we needed. So this is our first step in creating this algorithm. We need to build a hash map where our parent is going to be stored as a value and our key is going to be our node, which we currently are. So since now the binary tree is going to stay the same, right? But we're building this hash map representation, which could be interpreted as this graph right here almost, because we have bidirectional arrows right now. So when we have both directions, when we can go from 5, we could go to 6, or from 5, we could go to 3, we create ourselves another problem. We have a potential problem that we visit the same node twice. So that's why we also need a set. A hash set, where we're gonna keep the nodes that we visit, and we're gonna add these nodes in the hash set. And in case if we already seen it in the hash set, we're not gonna add it into our queue anymore. So with that being said, let's do a little recap. So we're gonna use BFS. We're gonna have a hash map, which is gonna store our parent node. We're gonna have a set to see if we've visited that node. And since this is a BFS and BFS has a queue implementation, we also gonna have a queue. So let's imagine this now. Let's go through an example and then we're just gonna jump into the code. So imagine that we are firstly adding 5 into our queue. This is our queue and we're adding 5. And this is our set. So since we visited this 5, we also gonna add it to our set. So right now what we need to do, in a normal BFS, we need to add we pop this 5 from the queue, we pull this 5 from the queue, and then we add its children, right? So we're gonna add 6 and 2, and also we're gonna add them into our set. And now we can also add its parent, right? There are only 3 directions from this 5 where we can go. We can go to children, because this is a binary tree, and its parent. So we're gonna look into the hash map, look for this root, which is 5 in this case, and we also gonna add 3. And we also gonna add 3 to our set. So you see right now, we performed the first level. This is the first level. So we'll have a variable called level, which we could start at 0. So after we added all these elements into our queue, then it means that our level is 1. What level do we need? We need level 2. So again, after we're doing this, we're popping this 6, we're pulling this 6 out of the queue, and we're gonna add its children. But its children, there's no children right here, right? And here's where our set comes useful, because we would want to add its parent, which is 5 in this case. But we're not going to add it because we already seen it in the set. So we're not going to add anything. Then we're pulling this 2, and now we're going to add its children into our queue. So now we have 7 and 4. And again, we would add its parent, but its parent it's already in the set, so we're not going to do it. Then we have our last 3 right here, and we're gonna remove it, and there's nothing as a parent. As a parent, is null right here, right? And we only have 1 children, so we're gonna add this 1. And after this iteration, we're gonna increment our level to 2. So you see now that basically what we've done right now is exactly our answer. This is exactly what we need to return. 7, 4, and 1. And we could even simply check if our level is equal to Q, we're just gonna return whatever we have in the queue at that moment. So that's it for this problem. Let's go super quickly and code it out so you could see how it will look in the code. So we said first we're gonna need a result, right? Since this is the main output that we need to return. So we could have a list of integer called result, and it's gonna be a new array list. And let's perform a basic check. If our root is equal to null, then we have no tree, right? So we could just return our result. So if our root is equal to null, then we could just return our result. Good. So now we said we need a few other things, right? So we need a hash map, which is gonna hold basically integers and integers, or we could even have a tree nodes. And tree nodes, we're gonna store the root and the parent. So let's do tree node and tree node, and we're gonna call it map. Good. So now what else do we need? We said we're gonna need a set, right? We're gonna need a set which is gonna store all the nodes that we're visiting. So we could have a set which is gonna store tree nodes, and let's call it visited. Good. So right now, what else do we need? Since we're doing a BFS, we also need a queue, right? Which again is gonna have tree nodes in it. Nice. So we kind of like did all the pre-requirements right now. So first thing that we have to do right now, we said we need to build this map. This map right now does not contain anything. So let's have a quick other method right here, private, and we could call it, we could have a void method and we could call it build map. And we're gonna take a tree node, which is our root. We're gonna take a tree node, which is our parent, which we don't have in this case, in the first iteration since we're starting at the root. And we're gonna we take a map, which is gonna get a tree node and a tree node, and let's just call it map. So the first thing we have to check is if our root is null, right? So if our root is equal to null, then we don't have anything, so we could just return. And then what we can do is we can put into our map, so we'll have map put. So we'll put our root. For example, if we're at 5, we're gonna put our root and our parent, which we're gonna get from the recursive call. So we're gonna put our root and our parent. Root and parent. And now we can call this recursive function again, build map, and we're gonna call it on the root.left and our root, and we're gonna pass also our map. And we're gonna call this recursive function on the root.right as well. And we're gonna pass the root and the map. So you see what we're doing right here. Initially, when we're gonna call this method in our main method right here. So actually, let's do it right now. So let's call this build map method. So we're gonna pass root first, and then null, and then our map. So why are we passing null first? It's just because when we started the root 3, there's no parent, right? So it's a null node. So we're gonna pass it with null node. And the first thing, we're gonna put our root, which is 3, and null. And then we're gonna go ahead and put our root.left, which is 5, but we're still at the root. So we're gonna put 5 and 3, 1 and 3. And then we're gonna move, and then we're gonna put 6 and 5, 2 and 5, 0 and 1, 8 and 1, and so on. So this is the method that gives us the maps. It gives us the reference to our parent nodes. So once we've done this, pretty much the problem is just a normal BFS traversal. So let's go ahead and let's add to our queue. We're gonna add our root, or we're gonna add our target, because we're starting from 5, right? So our BFS, imagine like we're gonna do circles around this 5. So we're gonna add our target, and let's have another variable. We said a level, and this level is gonna be equal to 0 first. Once we're right here, this is level 0. Good. So now, while our queue is not empty, this is just normal BFS traversal. So we have some operations to do here. Let's get the size of the queue first. And once we got the size of the queue, we are going to process all the elements that are in the queue at that moment. So while size minus minus is greater than 0, so now we are pulling the first node that is in the queue, right? So we added 5 to the queue. Let's pull this 5 and let's add its children, which is 6, 2, and its parent, 3. So let's go ahead and create a tree node, and we're gonna call it current equal to queue.pull. So imagine this current right now is 5, right? So we could check, and we can also gonna add it to our set, right? So we're gonna add it to our set and visited add current. So right now 5 is in our visited. So after we've done that, we need to check, is this the level that we want? Maybe k is equal to 0. So all we have to do is return 5. So we could check if our k is equal to level. In our result, we could just add result add current.value. And then that's all, like if k is equal to 0. But if it's not, we keep going. So let's get the parent first. So let's get the parent of this 5. So let's create a new node, tree node parent is gonna be equal to map get current. So you remember when we were right here, this is our map, and we're at this 5 right here. All we have to do is just look for this 5 in our keys and get the value, which is the parent. So we got our parent right now, and now all we have to do is add these 3 nodes to our queue. So if my parent is not null, and we said like if we see this parent in the visited set, we're not gonna add it, right? So if my visited does not contains my parent, then I'm gonna add it into my queue, right? So queue add parent. And the same thing exactly, I'm gonna do the same statement. I'll do it for left and right children. So I will do exactly the same thing, with the exception that right now we're gonna check if current.left is not equal to null, and visited does not contain current.left. I'm gonna add current.left to the queue, and exactly the same thing I will do for current.right. So right now we added all the surroundings nodes of the target. So right now 5 was target, we added everything that was surrounded. So after we added everything that was surrounded and we exhausted all of them, we know that we're gonna increment our level because we're gonna go 2 levels down. So at the end of this while loop, we could just do level plus plus. So we're incrementing our level, and after the whole loop is executed, all we can do is just return result. because in this case, right now, in this case, if k is equal to 2, is gonna add everything. And we could probably even stop this loop for sooner. Right now, the way I wrote it is just gonna, I just realized this. So right now it's just gonna add all the nodes, but we can stop this loop. Probably we could have another condition right here while k is less than greater than 0, and then we're gonna decrement k. So we only execute this loop. We're only gonna add 2 levels to my queue. But this will work too, but time complexity wise is the same, but we could just save us some time. For example, if we have a very, very large binary tree and our k is equal to 0, I don't have to perform all these operations. So it will save us some good amount of time. So let's give it a try. I think I am having a little error right here. Just because my map okay, because I don't need to add the map on the recursive call. Yep, so that's it for this problem. Time complexity wise, so we're visiting basically, in the worst case scenario, we're visiting every single node. If our k is equal to the largest branch, we have to visit every single node. So that would be O of n. And space complexity, so we're adding all the nodes into the queue, and we're also adding all the nodes into the set into our visited, and we're also creating our hash map. So that's still constant O of n, just because we're not multiplicating, we're not adding anything exponential. So that's it for this problem. If you have any questions, please let me know. Don't forget, if for any problem they have, we might have a solution. So, or actually we do have a solution. Yep, that's it for this video. See you in the next one.